Hello viewers, in today's session we are going to discuss another important problem from limits, and in this session we are going to evaluate this limit where we have limit x tends to 0 positive. This positive sign shows that we have to find out the right hand limit of this function, that is 1 plus 2 over pi square tan square square root of x raised to pi over 4x, right? So let us start and let us call this limit as L. Now here we'll first assume that this function, that is 1 plus 2 over pi square tan square square root of x is f1x. So let us assume this function as f1x and this function as f2x, that is pi over 4x, and here we have f2x. So now this limit takes the form limit x tends to 0, and here we have the positive sign, and here we have f1x raised to f2x, right? Okay, so now let us first find this limit, that is L1, that is limit x tends to 0 positive f1x. So we have limit x tends to 0 and f1x is 1 plus 2 over pi square tan square square root of x, right? Now when x tends to 0 from the right of x is equal to 0, for example here if we take x is equal to 0, then we have to find out the right hand limit of this function. So we are approaching from the right of x is equal to 0. So here when x tends to 0, then we can see that this expression, that is tan square square root of x, it tends to 0 because x tending to 0. So tan square square root of 0, so we have tan square 0 and this tends to 0. So now the value of this limit L1 is given by 1 plus 0, because here this entire term it tends to 0 because tan square of square root of x tends to 0 when x tends to 0, right? So we can also write here 1 plus 2 over pi square and tan square square root of x, it tends to 0 as we have seen here. So this is 1 plus 0, that is equal to 1. So the value of this limit is equal to 1. So now let us find out the limit L2, that is limit x tends to 0, and here we have the positive sign, and f2x. f2x is pi over 4x. So we have limit x tends to 0 positive, and here we have pi over 4x. So we can now write pi over 4x in front of the limit notation. So we have limit x tends to 0 positive, and here we have 1 over x, right? So here if we take x is equal to 0 plus h, where h is a positive quantity and h lies between 0 and 1. So when x tends to 0, then h tends to 0. So we can also write this limit as limit h tends to 0, and here we have x is equal to 0 plus h, that is simply h. So here we have h. So now this limit tends to infinity, because when h tends to 0, 1 over h tends to infinity. So we have pi over 4, and here we have infinity. So this entire term, it in this term is not defined, right, or infinity. So we have seen that the value of this limit is not defined. So now let us draw an important conclusion here. So here we have seen that whenever we have a limit of this form, that is limit x tends to a f1x raised to f2x, and the individual limits, that is L1 is the limit x tends to a f1x, this limit is equal to 1, and L2, that is limit x tends to a and f2x, this limit is not defined. Then these type of limits can be evaluated by using this expression, that is e raised to limit x tends to a, and then we have f2x and multiplied with f1x minus 1, right? So here whenever we have a limit of this kind, limit x tends to a f1x raised to f2x, and here our problem is similar to this one, and the conditions are the limit x tends to a f1x, which we call L1, is equal to 1, and we are taking L2 as limit x tends to a f2x, and this limit is not defined. Then this type of limit can be evaluated by using this expression. So here we have the exponential number, so e raised to limit x tends to a f2x and f1x minus 1, and here we see that both our functions f1x and f2x are satisfying these two conditions, right? So let us now apply this rule to get the value of this limit L. So now the value of this limit L can be written as e raised to a limit, and here we have x tends to 0, and here f2x is pi over 4x, and then we have f1x is 1 plus 2 over pi square, tan square root of x and minus 1, right? So now we have e raised to limit x tends to 0 positive, and here we have pi over 4x, and now we can cancel this one with this one, so we have 2 over pi square tan square root of x, right? Now this pi and this pi get cancelled, and here we have 1, here we have 2, so now we have limit x tends to 0 positive. Now here we are left with 2 and pi, so here we can write 1 over 2 pi, and here we have tan square root of x over x, right? So now we can write 1 over 2 pi limit x tends to 0, and here we can now write tan square root x over this x can be written as the square of root x, right? So now we can write e raised to 1 over 2 pi limit x tends to 0, and here we can now write tan root x divided by root x, and we can take the whole square, right? So here we have tan square root x, here we have root x square, so combining these two terms, here we can take the whole square, right? Now see, this limit is of the form limit theta tends to 0, and we have tan theta over theta. So this is a standard result in limits, and this limit is equal to 1, right? And here theta is equal to square root of x. So when x tends to 0, from the right of x is equal to 0, then square root of x also tends to 0. So now we can rewrite this limit as 1 over 2 pi, and limit here we can write root x tends to 0, right? And here we have tan root x over root x, and this is the whole square. And now this limit is equal to 1, so we have 1 square, so we have 1 over 2 pi, and here we have 1 square, so this is equal to 1 over 2 pi, right? So the value of this limit L is equal to e raised to 1 over 2 pi. So now let us consider one more example. So let us consider this limit x tends to 0, 1 plus tan x or divided by 1 plus sin x raised to square root of pi divided by sin x, right? So here if we compare this limit with this one, that is limit x tends to a f1x raised to f2x, then f1x is given by 1 plus tan x divided by 1 plus sin x, and f2x is given by square root of pi divided by sin x. And here the value of a is equal to 0, right? So we have to find out the value of this limit. So let us call this limit as L, and here let us first find L1, that is limit x tends to a f1x. So we have limit x tends to 0, and for f1x we have 1 plus tan x divided by 1 plus sin x. So now this limit can easily be evaluated, because we can write limit x tends to 0, 1 plus tan x, and here we have limit x tends to 0, and here we have 1 plus sin x. So now we have 1 plus limit x tends to 0. Here we have tan of x, and here we have 1 plus limit x tends to 0, and here we have sin x. Now see, when x tends to 0, then tangent of x also tends to 0, and similar is the case with sin x. When x tends to 0, sin x also tends to 0. So now these two limits are equal to 0. So we have 1 plus 0 over 1 plus 0, that is 1 over 1, that is equal to 1. So the value of the limit L1 is equal to 1. Now let us calculate L2. So we have L2 limit x tends to a f2x, and here we have limit x tends to 0, and f2x is square root of pi over sin x. Now here we can write square root of pi in front of the limit notation, and we have limit x tends to 0, 1 over sin x. Now see, when x tends to 0, then sin x tends to 0, right? So this limit it tends to infinity, that is when x tends to 0, sin x tends to 0. So 1 over sin x, it tends to infinity or not defined, right? So here we have square root of pi, and here this limit is not defined. So we have L2 is tends to infinity, that is L2 is not defined, right? So these two functions f1x and f2x satisfies the condition, that is L1 is equal to 1 and L2 is not defined. So we have just seen that whenever we have a limit of this sort, then L1 is equal to 1 and L2 is not defined, then the value of this limit is given by e raised to a limit x tends to a, and here we have f2x multiplied with f1x minus 1, right? So the value of this limit L can now be written as e raised to limit x tends to 0, and f2x is square root of pi over sine x, and here f1x is given by 1 plus tan x divided by 1 plus sine x, and here we have minus 1. So now we can simplify. Here we can write a square root of pi, and here we have limit x tends to 0, and here we have 1 over sine x, and simplifying this term we have 1 plus tan x minus 1 minus sine x, multiplying this 1 with 1 plus sine x, and here we have 1 plus sine x, and here this one get cancelled, and we have e raised to square root of pi, limit x tends to 0, and here we have 1 over sine x. Now we are left with tan x minus sine x divided by 1 plus sine x, right? Okay, so now here we can write tan of x as sine x over cos x. So we can now write e raised to square root of pi, limit x tends to 0, and we have sine x over cos x minus sine x, and in the denominator we have sine x, and here we have 1 plus sine x. So now we can cancel this sine x by taking sine x common in the numerator. We have e raised to square root of pi, limit x tends to 0, and we are left with 1 over cos x minus 1 divided by 1 plus sine x. So now we can write this limit L as e raised to square root of pi, and we have limit x tends to 0, 1 minus cos x divided by cos x, and here we have 1 plus sine x, right? Okay, now see, when x tends to 0, then cosine of x tends to 1, because cos of 0 is equal to 1, and when x tends to 0, sine of x tends to 0, because the sine 0 is equal to 0. So now we can write this limit L as e raised to square root of pi, and see, here we have 1 minus 1, and because limit x tends to 0, cosine x is 1, and here we have again 1 and 1 plus 0, right? So what we have done here, limit x tends to 0, cos x is 1, here we have 1, so we have 1 minus 1, and limit x tends to 0, cosine x, so this is 1, and limit x tends to 0, sine x is 0. So here we have e raised to square root of pi times 0, because 1 minus 1 is 0. So we have now here e raised to 0, and here in the denominator we have 1 plus 0, that is 1. So 1 times 1 is simply 1. So we have now e raised to 0, that is equal to 1. So the value of this limit L is equal to 1.